Today we're going to be going over Unit 1.2. We'll be talking about mass spectroscopy, which involves isotopes, the actual process of what mass spec is and the output, and average atomic mass. So first we're going to talk about the shell model of an atom. It's not the most accurate model of an atom, but this is really where we get the point across of what contributes to mass and what contributes to volume. So you know that an atom is made up of protons, neutrons, and electrons. The protons and neutrons are concentrated in the nucleus, and they make up the most mass of the atom, but they take up the least amount of volume. Around that nucleus of protons and neutrons, we have electrons that have a negative charge. These make up most of the volume of the atom, but the least amount of the mass. So we say that they don't contribute to the mass. Electrons do have a mass, it's just very small relative to protons and neutrons. So when you consider sig figs and the actual contribution that they make, it's very small. With this, we also notice that atoms are mostly empty space. There's a lot of space around there, and also keep in mind that these electrons are moving around rapidly, so there's a lot of empty space in an atom. So this slide kind of sums up all that we see based on, or all that we determine, considering the shell model of an atom. Nucleus is very small but positively charged. The negatively charged electrons are very tiny and surround the atom, and an atom is mostly empty space. This sums up the charge and mass of different subatomic particles. So protons and electrons have the same numerical charge, 1, but they have opposite signs. So a proton is positive and an electron is negative. A neutron has no charge, it is neutral. Then when we consider mass, protons and neutrons have essentially the same mass. If you were to carry over a lot of decimals, you would notice that they are different, but with rounding, they're essentially the same value for their mass. And that is in AMU atomic mass units, because we were talking about subatomic particles, which are extremely, extremely small. Electrons don't really have a mass until 4 decimal places out. So if we were around to, the ones place, as these are, it would essentially be 0. Here we have how atomic and mass numbers can be represented in a chemical symbol. So sometimes they will give you an isotope specifically of an element in this format, and you are basically able to determine the subatomic particles in this specific isotope or this specific atom. So A, this little superscript before the chemical symbol, is the mass number. It's equal to the number of protons plus the number of neutrons. Oh, did not mean to, let me go back. Mass number and atomic mass, it's really easy to mix them up because they are similar, but mass number is specific to an isotope, sum of protons and neutrons in that specific atom, whereas atomic mass is an average, a weighted average of the mass number of different isotopes. So we'll talk about that a little bit later. And then in the little subscript before the chemical symbol, we have the atomic number, which is equal to the number of protons. And if we have a neutral atom, which if it wasn't neutral, we would have a charge up here, it would be equal also to the number of electrons. So here we have carbon 12. The atomic number, 6, tells us the number of protons and electrons. To determine the number of neutrons, we have to do a little bit of math. So remember that the mass number up here is the sum of protons and neutrons. So to find the number of neutrons, all we have to do is subtract 6, number of protons, from this sum, and we get 6. So in this isotope, we have 6 neutrons, 6 protons, and 6 electrons. Isotopes of an element always have the same number of protons. Your number of protons determines the identity of what element you are dealing with. So if you change the number of protons, you actually change the identity of the element. Isotopes are the same element, so number of protons are always going to be the same. Same thing with electrons. If you change the number of electrons, you go from having a neutral atom to an ion. So unless you do that, your number of electrons are going to be the same. So the only thing that really just differs with isotopes is the number of neutrons. Isotopes of an element exhibit similar behavior, so they react the same with other elements. And so if you consider water, you're equally likely, and we'll go into that a little bit later. So not equally likely because they are different, they are around in different proportions, but you could have hydrogen 1 binding with oxygen or hydrogen 2. Both of them react the same with oxygen. One isn't more likely to react with oxygen when you consider their makeup. When you consider their abundance, then yeah, one is more likely to be found. We'll get into that. Same with carbon. For carbon dioxide, carbon-14 and carbon-12 are both present in carbon dioxide. One doesn't make up carbon dioxide exclusively, and the other won't, or anything like that, because isotopes behave the same. So here again, we have carbon-12, which we had 6 protons, 6 neutrons, and 6 electrons. If we have an isotope, carbon-14, you'll notice here, the number of protons are the same because it's still carbon. The number of electrons are the same because it's still a neutral atom. The only thing that changes is the number of neutrons. Go ahead, take a second and pause, do the math to find the number of neutrons. When you do that, you should find that there are 8 neutrons. 14 minus 6 equals 8. Here we have hydrogen 1. Hydrogen 1 has 1 proton because it's hydrogen, 1 electron because it's neutral, and here the mass number is equal to 1. So if you find the number of neutrons, you would be taking 1 minus 1, which equals 0. So hydrogen 1 actually has no neutrons, which it's still stable. Hydrogen 2, you have still 1 proton, 1 electron, and this time 2 minus 1 neutrons, so you'll have 1 neutron. With atomic masses, AMU, or atomic mass, was basically built around the carbon-12 atom. So the nucleons in all atoms other than carbon-12 are not exactly 1 AMU. If you study nuclear chemistry in another course, you'll learn that mass is converted into energy when nucleus binds together in accordance with the formula equals mc squared. So every other atom is basically measured on a scale relative to C12. So they basically built this atomic mass scale all around carbon-12. The atomic mass that you see on the periodic table is actually a weighted average of all the isotopes of that element. Okay, so the weighted average of the mass of those isotopes of that element. A weighted average is different than the typical average you use to find like your grade or something. Weighted average, you're going to have the mass of that isotope multiplied by its abundance, which is typically a percent out of 100. So usually this percent is converted to a decimal. An average mass of any large number of atoms of a given element, so if you have a large sample of an element, the average mass is always the same for that given element. Okay, so if you had 2 different samples, the average mass of those 2 samples would be the same. So the ratio of the ratio of isotopes for any element is going to be constant. So whether you have a sample of hydrogen in one room and then a can in another, the ratio of isotopes within those 2 samples are going to be the same. Here we have mass spec, which basically helps to compare the masses of isotopes. So you have a sample here that you inject, typically it's gaseous or vaporized, and then you have an ion accelerator, so that accelerates the sample through this tube, and the magnetic field here is really where things start to happen. So when you apply a magnetic field, it's going to cause the individual particles to be deflected, typically away from the positive charge towards the negative charge. So when we have an ion, we're basically, when we're making an ion here, we're basically measuring the nucleus, because remember, the nucleus makes up the mass of that element. So the nucleus overall is going to be positive. Since like charges repel one another, positive is going to deflect and negative is going to attract. The lighter something is, the easier it is to kind of deflect it. So it's going to be deflected more if it's lighter and less if it's heavier. And then this deflector plate, basically equal masses. So here it would be a lighter one because it moved more, but they would hit the same spot, and then the heavier ones would hit the same spot. And this deflector plate basically measures out how much of each isotope that you get. So it basically recognizes when it is hit. Here we have a problem. So with the mass spec, that machine usually gives you some sort of output that tells you the percent in the sample of each of these. So you'll notice that this silver sample has two isotopes, 109 and 107. And you'll notice that the relative number of atoms, they add up to 100. So 51.84 plus 48.16 is going to equal 100. So essentially, 51.84% of the ions detected were silver 107. 48.16% were silver 109. The mass value, or the atomic mass, you could say, I know it's not the atomic mass on the periodic table, for 109 is 108.90476. You'll notice it's close to 109, but not exactly 109. If it doesn't give you that value of what the actual mass value is, usually it's okay to just round to 109 because, again, it is so close to it. We want to find the mass value for silver 107. With this, we do need the periodic table. With the periodic table, we know the average atomic mass, or the atomic mass that's reported on the periodic table for silver. So that is going to be the value that we use when the weighted average is found, essentially. So we can use that because it's given on the periodic table. And again, the relative number of isotopes is going to be the same with any given sample. So here we have the atomic mass of silver 109 times its percent abundance. Convert that percent to a decimal, just to make your calculation a little bit easier. We're trying to find the mass value for silver 107. You could replace it with X as well if you would like that. And multiply it by its percent abundance, 51.84%. This 107.87, that is the atomic mass that comes straight from the periodic table. So now we can do some math, rearrangement, algebra to figure out what the mass value for 107 will be. So when we do that, we find that the mass value is 106.9 AMU. You can also figure out what element a sample is using the periodic table and the output that the mass spec gives you. So here we have the average atomic mass of an element in question, and we want to identify that element. So the mass number, 35 of whatever this element is present in a 75.78% abundance, whereas the isotope 37 is present in a 24.22% abundance. They give us the exact mass values, so we don't have to round to 37 and 35. We have these values here that we can replace to be a little bit more accurate. So we are going to multiply these mass values by their percent abundance to find the average, the weighted average, which is the atomic mass reported on the periodic table. So when we do that, the mass value times the percent of abundance added together, we find that it's 35.45 AMU. Now I go to the periodic table. Is there anything close to this value? Yes, it's chlorine. It's the average atomic mass that is given on the periodic table. Okay, sometimes it's not exactly the same, but it's relatively close. And in that case, you would round a little bit to give your best estimate, not really guess because it's based on data. Okay, so that's it for the 1.2 notes. Please let me know if you have any questions.